Okay, so now we're going to talk about prime numbers, which is something that on the surface looks like it has nothing to do with exponentials or logs, right? Can you list some of the first prime numbers?
2, 3, 5, 7, 11, 13, 17.
Okay. Good job. The number of prime numbers less than n, if you just take a, this works better for larger numbers, but it's a good approximation. The number of primes less than n is approximately n over ln of n, the natural log of n. So the inverse of the e to the x. Okay, let's see. So we try to understand how many powers of e go up to n. Okay, that's what ln of n is. And we just take our number and divide by that. That's about how many primes there are. This is a really fascinating theorem. And as this number, so this has been proven and people have understood this, and it's really fascinating. You wouldn't think these prime numbers have anything to do with e or logs, but somehow they do. Nobody knows any patterns in the prime numbers, but mathematicians have been able to figure out about how many there are below a number. Pretty cool, right?
Yeah.
Now here's an unsolved problem. The number of twin primes, like 3 and 5, 11 and 13, 17 and 19.
Ones that
differ by 2. I guess I skipped 5 and 7, didn't I? But so nobody knows for sure about these twin primes, but people suspect that the number of twin primes is approximately equal to n divided by ln of n squared. Okay? And this would mean there would be infinitely many. But nobody knows, by the way. No one knows. And in fact, just last year, a mathematician at New Hampshire named Zhang made a huge step. He proved that there were infinitely many primes whose difference was at most, 70 million. And a bunch of other mathematicians have worked it out even lower, that there are infinitely many primes who differ by, at most, 600. But the number of twin primes less than n, people think is about this. In fact, it's about 1.25 times this, but it's about that. This was conjectured in the early 1900s. Nobody knows. It's an unsolved problem. Pretty incredible, right?
Yeah.
And there's one other amazing theorem about prime numbers that involves logarithms. So first we've seen n over ln n, and then n over ln n squared. Now we're going to see ln of ln. Whoa. So the number of divisors. This is something called the Erdos-Katz theorem. The number of divisors is approximately ln of n.
Wow.
Now that's incredible, actually. So this is a hard theorem to even understand. It's about statistics. But it says if you take a number like a billion, ln of n is about 3. So it says for numbers around a billion, they have about 3 prime divisors on average.
Wow.
Yeah, wow. This is an amazing theorem. And again, counting the divisors, counting the prime divisors, again, logarithms show up. So this is just pure math. So forget about like mortgages and interest and calculating stuff like that. Just talking about prime numbers, logarithms show up everywhere, and there's some cool, really cool unsolved problems just about prime numbers that no one knows about. So that's a kind of a fun use of logs. I'm going to do one more, okay?
All right.